I'm glad to be joining you on ACCB 20. My name is John and I will be presenting our work on evaluating Bayesian neural networks against out-of distribution adversarial examples. This is a joint work with Arjun, who is a postdoc at the UCD, and Brian, who is my supervisor. The contributions of our work show that Bayesian neural networks do indeed improve the out-of distribution detection task, but they cannot mitigate adversarial noise attacks. Essentially, we also show that the OoD detection is much harder when there is an overlap between classes on the in-distribution and out-of-distribution examples, and techniques such as outlier exposure might not be such beneficial on such occasions. Defense techniques degrade accuracy on the clean test, but they do improve robustness, and occasionally they improve the out-of-distribution detection. This presentation has two parts. The first part has to do with the evaluation of out-of-distribution detection, and the second part has to do with the evaluation of adversarial defenses. The goal is to evaluate the effectiveness of marginalization on OoD and adversarial examples. I'll start with a simple motivational example. We have an underlying classifier which has been trained with random rotations minus and plus 30 degrees and with random horizontal and vertical flips. At test time, we actually evaluate the same classifier while we rotate the underlying instance between 0 and 180 degrees. As we can see that the underlying classifier is misclassified with really high confidence. So you can see that this is quite problematic for real-world applications, and especially medical applications. Anything here beyond the 30-degree angle constitutes as an out-of-distribution example. So the first part, evaluating the out-of-distribution detection. For the first part, we use the following datasets to train our models, the metrics which we evaluated the models, and the underlying models. For all the models, we use the same architecture in order to avoid discrepancies. Here we present the accuracy of each model across the different datasets. As you can see, there is not much discrepancy between different models and datasets in regards to the accuracy. Table 2 presents the results of the evaluation of the OoD detection task. This table shows that SWAG is the best performing model, with DPN being the second one, but this can be quite misleading. That's why we follow up with the following ranking on all the models against all the metrics, and what we find here is that DPN actually is the best performing model, with SWAG coming the second best. SWAG is the underlying model which can provide the best trade-off between accuracy on the clean test set and the OoD detection task. The second part of our talk has to do with the adversarial examples and the robustness analysis. So here we ask two simple questions. Can marginalization detect adversarial examples? And could simple defense mechanism outperform or improve them? Again, here are the metrics that we use for this evaluation. These are our data sets. So we use the CIFAR-10, the clean test set, the adversarial corrupted, and different test sets as OoD detection, the underlying models, and the defenses that we have considered for this evaluation. So what we see here is that on the clean test set, without any defense, you get the best accuracy overall. This could also be indicative that also prior works have shown that deep neural networks actually overfit on non-robust features, and that might be an explanation here why we see such discrepancy between the accuracy on no defense versus the defense techniques. Second, on the corrupted with adversarial noise dataset, what we see here is like the randomized smoothing is the best performing defense technique. Table 6 shows the out-of-distribution detection. Here we have CIFAR-10, which has been corrupted with adversarial noise, and what we see here is like the best performing defense is top K. And again, here we have out-of-distribution where we present different data sets, and in this instance the best performing defense technique is MMLDA. As a summary, we would like to point out that marginalization does improve OoD detection, but does not possess the ability to cope with adversarial examples. Adversarial techniques overall degrade accuracy on the clean test set, but at the same time they actually robustify against attacks and occasionally do improve the out-of-distribution detection. Finally, consider a simple example where we have three classes with a varying standard deviation between the classes. If we have a single underlying model which uses radio activation, then the decision boundary should be something like this, where we separate the three classes. Instead, what we see in these examples here, like if you actually change your underlying objective laws, then that can actually change the decision boundary in ways that you cannot anticipate. So that would change, that would result in changing the decision boundary completely differently than what the activation function would imply. So that would be something to consider for the viewers when we move forward in actually designing our models and the implications of each of the choices that we make in these models. Thank you for your time, and thank you for attending this presentation.